So once we've determined that it's possible to throw faster and faster, and your pitch will land not only further forward, but further around the Earth, because the Earth is not a flat surface, it stands to reason that if we go fast enough, we should be able to throw and miss the Earth entirely. Let's give this a try, purely experimentally. Newton does this mathematically. Oh, did we make it? Did we make it? Beautiful. Orbit has been achieved. What happened to the pitcher? Why?
He got hit from the ball.
He got that hit in the back of the head by a ball that was traveling 7,100 meters per second. So apparently, the reason we don't send actual baseballs into orbit every time Zaki pitches a no-hitter here is not just because we have trees and mountains and tall buildings in the way. It's because you only do this, fall for the ground and forget to land, just throw it at the ground and miss if you're going more than 7,000 meters per second. Now, as long as we're here at Newton's Mountain, let's try going a little bit faster and see what happens. What shape was that orbit?
Circle.
That was a circle. Is this a circle?
No.
Ooh.
More
Oh, it was like a parabola. Does it still look like a parabola?
No.
No. 3, 2, 1. Oh, weird. What is this shape? It's not a perfect circle. A perfect circle would have been like over here. And it's not a parabola because it comes back. Yeah. What is the official math name for that like an egg thing?
An oval?
Ooh, very good. Oval is the art name. The math name is ellipse. If you haven't started drawing this and taking notes, do so now. While you are starting to draw your little planet with your circle and orbit and with your ellipse orbit, I'm going to try a few faster speeds and see if we get the same thing. What do you think? Do you think it's coming back?
No.
I don't know, it's taken a while.
It should come back, right?
Well, we learned that the gravitational field never really goes to zero, it just gets weaker and weaker the further away you travel from the planet. Gosh, it seems to be going very, very slowly. Oh my goodness. It's not coming back. So apparently, there is a speed for which you can go so fast that by the time it's time to turn around and come home, the gravitational field isn't strong enough to bring you home. We want a better way to figure that out than sheer experimentation. Notice it's taking an awfully long time. Wherever it is, it's going. It's certainly taking its sweet time about it. And there it is, there it is. What do you notice about the speed right now as it's coming back?
It's going faster when it's closer to the Earth.
Oh.
Because it's closer to the gravity.
Hey, there we go. Gravitational field is stronger closest to the Earth, and that seems to be correlated with the fact that the now satellite instead of baseball is going faster. So we have seen several different shapes here. And I'd like everybody to draw them in your notebook exactly the way Newton did. And I'll get you an image for that. Newton's Mountain looks like this.
It's inside of it.
Here, Newton is trying to draw the contours of the Earth, like mountains and lakes and rivers and things. He's launching. In his case, he said he was shooting a cannon off the mountain rather than pitching a baseball. He has path D, where you pitch fast, path E, where you pitch faster, path F, where we're in business. And over here, path A, we've got the first circular orbit. Now, this version, you can see that the circular orbit, if you pitch faster, you will get an elliptical orbit as well. And if you pitch fast enough, you will be able to go out of orbit. Once you've got your Newton's mountain sketched and labeled, I want to talk for a little bit about math, because all these shapes that we've noticed experimentally in the orbits are family.
What is the ball that was thrown like it was 9.9 kilometers per second?
We're going to call that escape velocity, and I hope to have a formula for it by the end of the period.
Is it because it anything to do because it's above 9.8?
No, it is. It has to do with the mass and the radius of the planet. And remember that G equals GM over R squared also has to do with the mass and the radius of the planet. You notice I was doing this by experimentation. I'm being quite truthful. I'm used to working with a different sim that's black and white. And on that sim, the escape velocity for the actual planet we're standing on is 11.2 kilometers per second. So notice you saw in the sim controls for the mass of the planet.
Oh yeah.
The reason that you get different escape velocity at different places is because you're not necessarily standing on the surface. The third setting on this simulator, cheatsies, was pitcher height.
Oh.
1,500 kilometers. That pitcher had better be born and raised there, or he's going to need to be on the same kind of medication I take when I fly to Denver to deal with the low oxygen there. All right. Math lesson, going with the notes. The family that we're looking at here is called conic sections. And geometry was plain geometry at least, was worked out by the ancient Greeks. So by the time Kepler gets to Kepler's laws, he knows the conic section family when he sees it. The idea is all these shapes can be gotten if you slice through a cone. Step one, go nowhere. That's the point of the cone. You just stand there. Step two, crash on the surface. This is what they call a degenerate conic section in math. I prefer the physics term, you crashed. So we're going to start making a list here. At anything less than orbit speed, that's going to be anything less than we found somewhere in the 7,000 or 8,000 meters per second, depending on where on the planet you are, the shape is going to be a crash. Things started to get interesting at orbit speed. When you achieve orbit speed, then you get an orbit that looks circular. Kepler's laws say it's not really a perfect circle because nothing's perfect, it just looks like a circle. Okay, it looks like a circle. I'm going to make a note here in math ease for those of you in pre-calc. I'll explain in a minute. Now, we're more than orbit speed. However, we're less than escape speed. Now, we're getting an ellipse. planet at one of the two focus points of the ellipse. I'll explain that in a minute. Now, there are many different types of ellipses. For instance, there's the kind of ellipse that you have to wait 5 minutes for to see if the planet is coming back, and we're taking bets. And there's the kind of ellipse that really looked like a circle. It's like, is that an ellipse or is that really a circle? The measure of how long and squashy the ellipse is versus how circular it is called the eccentricity. Eccentricity is fancy grown-up E's for weirdness. A circle, by definition, has 0 eccentricity. It's not weird, it's perfectly symmetric. So an ellipse has an eccentricity that's more than 0, but less than 1. So an eccentricity of 0.03, who are we kidding? It looks like a circle. An eccentricity of 0.9 looks like a rubber band that you're about to shoot at somebody. It's so stretched you can scarcely see it's an ellipse at all. So, Eitan, you're in the passage, so you get to make our ellipse today. I did not touch the markers all morning. They're ready for you. Uncap one of those markers. And use the marker to pull the string taut.
Oh, wait.
Yeah. No, yeah, with the pull the string taut. Yeah, pull. Oh, but without breaking the tape. Breaking the tape is an eccentricity of 1. We're going to do that next.
Okay.
So before you break the tape, pull the string taut. Yeah. Now move wherever the string lets you go. Move to the right. There you go. And move to the left. All the way around. Yeah, keep going. And do the top side too. You may want to move the marker.
You mean like up here?
Yeah.
So,
There you go. That is the geometric definition of an ellipse. A circle is a shape that's equidistant from one point. That one point is the center. An ellipse is a shape that's equidistant from 2 points. Those 2 points are the focus points. I put tape on the focus points. So the planet would be here at this focus point. What's at the other focus point? Nothing, it's empty space. But doesn't an ellipse have 2 focus points? Yeah, that's math. Our point is, if the sun were over here, Pluto would still have the same orbit. But the sun isn't over there. Yeah, that's my point. But if it were, Pluto would have the same orbit. Do we care about that? No. Sun's over here. The sun is not the center. The sun is the focus. This is why Pluto, which has an orbit of very high eccentricity, can cut across Neptune and be slightly closer than Neptune is for a couple of decades before it goes back out. Now, what happens when you break the tape? That's an eccentricity of 1. It is terminally weird. It is so terminally weird, it is not even in the circle family anymore. The next conic section is a parabola. And that is what we are going to call escape speed. Now, parabolas are known for being big and curvy. They are not known for any kind of predictable straight line behavior. They go up, over, and out, up, over, and out. They have one focus point in a directrix, which doesn't do anybody any good. Nobody who wants to leave a planet really wants to go up, over, and out, up, over, and out. What they want to do is leave the planet going in a straight line. For instance, Mars Perseverance landed yesterday. Touchdown! It was epic. Our victory dance is several $billion more expensive than the victory dance of the NFL, but the epic touchdown was there. When we leave orbit, we want to go straight to Mars, not up, over, and out, up, over, and out, up, over, and out, and up on Pluto for all we care. A hyperbola has asymptotes. You've heard about these asymptotes in math class. asymptotes are not straight lines, but they're almost straight lines. If you go out at more than escape speed, like really, really more than escape speed, these lines will look straight. It won't just be up, over, and out. You get to go where you want to go in a hyperbola. Or in a spacer. A hyperbola has a focus point. The planet whose orbit you're leaving, but that focus point is exterior to the shape. Say what? You're leaving orbit, not going into orbit.
All right, instead of just experimenting, let's figure out at what speed we need to go in order to properly launch into orbit. The most basic orbit is a circular orbit. And we know from first semester mechanics that in order to go into any kind of circular path, you need a centripetal force. The centripetal force is not a real force at all. It's a net force. That means we need some other force to be the centripetal force. In this case, the picture is clear. The centripetal force, the force that's pointing in towards the surface of the planet, is gravity. Here's our desired orbit path, and here is the force of gravity. We used to call it down. We now know that down is no longer accurate because if you're in this part of the planet, gravity goes this way. But this is as center-seeking a force as anybody could wish. There it is, the force of gravity. And we know from Newton that the force of gravity is, pause this, look it up in your notes, it was on the quiz, GMM over r squared. Pause, look up in your notes. What is the formula for centripetal force? Ready? Found it? There. Solve this until it says V equals. The algebra is not so bad. There are at least two things you can cross out. You'll have two steps in algebra until you have V orbit equals at the end. Press play to check your work only after you've done it yourself. Ready? Have you done your own work? Well, there's two little m's. Those can be divided out. And there's one r in each denominator that gets rid of the squared. So, we have, as Zach said in class, v squared equals gm over r. Then you simply have to finish the problem. There we go. Put a box around the formula. This is the minimum speed you need to go into orbit at any place. The square root of g depends on the strength of gravity in the universe. M depends on the size of the planet you're orbiting. Over r depends on where you are. That means if you're further away from the planet, you don't have to go as fast in order to get into orbit. If you're closer to a big mass, then you need to maintain a very high speed in order to maintain orbit. What if you didn't bring enough fuel? What if your ship's not fast enough? What if you can't maintain a speed that's the square root of gm over r? Then you are scheduled to crash on the surface. It will be your fault for getting too close without having a ship that could go fast enough. Moral of the story, if you can't go that fast, stay far away. Notice that as r gets bigger, the speed you need to go gets smaller. If you go faster, if you go v is slightly greater than the square root of gm over r, then you will have an elliptical orbit. Now, let's talk about escape speed. We absolutely cannot do anything like the same algebra for orbit speed and escape speed. The whole point of being in an orbit is to be in the planet's gravitational field and use that gravitational field to give you a round trip. The whole point of escaping is to be out of orbit. You want to leave the planet's gravitational field, not use it. The planet's gravitational field is keeping you stuck where you are, in orbit. You have gravitational potential energy. Unfortunately, that potential isn't doing much for you. You want to take all of your gravitational potential energy from that gravitational field, and you want to get rid of it. Now, conservation of energy says you can't just get rid of energy. You have to give it away. You have to convert it to something. And I propose that we convert the gravitational potential energy into kinetic energy, since we saw that going faster broke us out of orbit. If this were first semester, we would know all the formulas for gravitational potential energy and kinetic energy. Kinetic is easy. That's 1/2 mv squared. That never changes. Gravitational potential energy, on the other hand, used to be mgh. And not all of those terms are relevant for outer space. For instance, if we are above Earth, like here, we don't call that h anymore. Usually, when we say we are here, we don't measure to the surface anymore. We measure all the way down to here. We call that the bottom, not this. What's this? Yeah, that's not H. That's the letter R. Okay. Okay, we can work with this. We can work with this here. Okay. So instead of MGH, we have MGR. Wait a minute. We didn't used to measure H from the middle of the planet's core. No, we measured H from the 3rd floor of the classroom in 314, or from the 2nd floor of your bedroom window if you were remote. We can measure H from wherever we want. If we want to measure it from the center of the planet, that's fine. Now, what about G? G used to be 9.8, but we found out that G varies where you go on Earth. And if you leave Earth, it changes completely. G on the moon is 1.78. G on Mars is like 3. Wait a minute. We have a formula for G. We do. Look up your formula for G and substitute it here. Once you have substituted the formula for G, you will see many, many nice things that cancel out. Multiply the 2 to the other side and solve for V if you please. Do all your work yourself. Press play only to check your work. Ready? Did you look up the formula yourself? If you did, you found that our formula for G, the strength of the gravitational field, was Gm over r squared. Bam! All right, that's already 1r down. And the m's, as we said before, you don't need to weigh in before launching into space. Multiply the other side by 2. And we have a formula that looks very similar to the one we had before. Trick question. Is escape velocity twice as much as orbit velocity? Is escape velocity twice as much as orbit velocity? Careful. It's not twice as much as orbit velocity. It's the square root of 2 as much. 1.414, that's 41% higher. That's why when you do Newton's mountain in the simulator, you'll get escape speed for the Earth's surface is somewhere around 8,000 meters per second, and then somewhere in the 11,000s, then you can break out of orbit and go elsewhere. If you go exactly the square root of gm over r, where r is measured from where you are to the center of the planet you're trying to break out of orbit, you will break out in a nice parabolic path. You will go up, over, and out, up, over, and out, without any particular pattern. If you go faster than the square root of 2gm over r, then after curving around for a while, you will approach a nice straight line and go wherever it is that you want to go.